First one is like after which what we just did with you. It's this very straightforward part. It says find the inverse for the matrix, for the diagonal matrix like so. The question 21 itself, it doesn't use this notation. It just gives you the matrix of this form, but this is my way of writing it. It's not like it's my way. Trust me, it's a conventional way of writing diagonal matrices. The yellow book doesn't use that. Actually, I'm not sure if it doesn't use that, but I think it doesn't. But I do. And given what we have discovered just now on the previous slide, the answer to this will be just immediate one-line answer, because every diagonal entry here is non-zero. We do have the inverse. And that inverse will be just a diagonal with all inverses in the corresponding positions. You can write this as in the canonical notations of a matrix. Here's my diagonal matrix for the inverse. You don't have to do any row echelon forms. Just simply knowing this fact, how you find the inverse for the diagonals will do. Even though actually if you do row echelon forms here, it wouldn't be too long. So in part A, this knowledge I just discussed with you, it doesn't give you much of the advantage time-wise. But in part B, actually, it will give you considerable advantage. Look at this. In part B, you say find the inverse for the matrix B, where this time matrix B is given like so. Look what I'm going to do. Given the knowledge we just discussed with you on my previous slide, I'm going to make this improvement of the statement of the question. I'm going to introduce two new matrices. First of them will be like this. I call it a matrix C, and it will be diagonal matrix with these entries, 1, 3, and -2. The other one, I will call it a matrix. I will call it matrix U, and that will be this matrix. So this is the one which resembles B a lot. It's just every non-zero entry in B, I just converted it. Every that entry I converted in 1. Now the connection between my C matrix, U matrix, and my B matrix, the connection is this. B is a C times U. Why do I see that? Because that's my previous knowledge. If I multiply a matrix by a diagonal one, it means I have to multiply every row by the diagonal entry. So if I multiply every row, if I multiply from the left, here's my diagonal matrix, which is on the left hand side. So I have to multiply every row here by these entries, 1, 3, and -2. That will be B matrix. As easy as this. That's the knowledge I drew from my previous slide. Okay, the other knowledge which I'm going to use, we haven't discussed that yet. I frame it as a lemma here in this bottom corner of my slide. Listen to this lemma. It says this: if you have two square matrices, such that they both individually invertible, that's what this writing says. There are inverses for each of them individually. This is a fact which will be useful in many other questions, but I'm using this one as an opportunity to present this fact right now. So we have two square matrices which are invertible. Then the lemma says the product of these two will also be invertible. A B product, it will be another square matrix. It will also be invertible, and not only lemma says that, it also says that the inverse will be connected with the inverses of the original A and B, like this. Pay attention to the different order of the factors this time. It's important change, and you can't do the other way in general. I have a proof for this lemma on the slide, but I will put it off for a while. I want to finish the computation of part B first, and then we'll look into the proof of this lemma. If you believe me that the lemma is true, I can use this lemma now, because look at this. I'm looking for the inverse of B. Inverse of B will be, given I can convince you that C is invertible and U is invertible, well, with C is easy business because C is diagonal. We know how to argue that the diagonal is invertible. Every entry should be non-zero, which is true in this case. But for U, it will require some effort still. But if I convince you that C is invertible and U is invertible individually, and I can find the inverses for them individually, all I will need to do then to find the inverse for B, just multiply them in the right order. So U inverse times C inverse. So let's just look at them individually first. The inverse for C, we know how to find that. It's a diagonal matrix with these entries. It's again the knowledge we draw from the previous slide. Inverse for U. How are we going to find inverse for U? Look at this way. Well, you can find it in many other ways. You can do it via row echelon form, for instance. But I'm going to show you the method which is based on this our knowledge of the effects of multiplying a matrix by the standard basis vectors. Look at this. If I use my notation for the standard basis vectors, I can say that the matrix U is the one which consists of the standard basis vectors in this order as columns. Third standard basis vectors goes as the first column. Here it is, goes as the second column, and the second one goes as the last column. It's a fair observation. You can't argue with that. I'm going to use this observation now to my advantage. Look at this. I'm going to looking for the inverse of U. In principle, it will be matrix consisting of some unknown columns yet. I'll call them U1, U2, and U3. My job is to identify these columns. Well, the inverse, if it exists, the distinguished property of that inverse is that if you multiply the U inverse with U in any order, in fact, but for instance in particular order, in this order, then the product will be identity. So the product will be identity. Here it is. Which is, if I use again my notation like so, it will be, in terms of my standard basis vectors, will be this matrix. On the other hand, listen to this. On the other hand, we know what happens if you multiply any matrix with any columns by the standard basis vectors, isn't it? This U3 will cut the third column out of this. It's a discovery we made with you, well, a few times already, on Wednesday and last week, I think, as well. So in fact, if I do this multiplication directly, then the resulting matrix will be the matrix with the same U columns, but in a different order. Because multiplying this matrix by this standard vector, standard basis vector, leaves this column, the other two will vanish. Multiplying this matrix by this standard vector will leave this column, the rest will be vanished. Multiplying this matrix by the last E2 standard basis vector will leave second column, and that's why we have my columns in this order. So effectively, multiplication by U of my any matrix, it's a rearrangement of columns in some order. But on the other hand, they should be identity. That's the property of the inverse. And that let me conclude that my U inverse is this matrix. First column should be E2 from here. Second column should be E3. And the last one should be E1. You can write this in the matrix notation. Here's my inverse. Now, at the final stage, by lemma, this is by lemma, my inverse for B will be the combination of inverses for C and U individually in the right order. Here's a combination. And again, we can benefit from the knowledge of the previous slide, because here my U is multiplied by the diagonal matrix. When you multiply something by a diagonal matrix from the right-hand side, it is simply multiplying the columns of that matrix by the diagonal entries. So I have to take this matrix, which is a U inverse, and multiply the columns here by these diagonal entries. So the inverse will be this matrix. How brilliant is this? In the whole course of the solution, I haven't made a single multiplication. Okay, I promise you the proof of the lemma for two reasons. It's a nice lemma just to see the proof. On the other hand, there are a few questions in the yellow book which you may do them by using the ideas from this lemma. That's why I'll prove the lemma as well. The proof is relatively easy. All you have to do is this. Because your job is to convince me that there is an inverse for this matrix AB, and the only way to do that is do something like this. You just give a names, even though it's a bit unfortunate name. Well, it is unfortunate because this C has nothing to do with this C. I hope you can, because CEP is, let me just change it. Let me just change it to something else. Let me just call it. Any suggestions? I don't like D because D goes for the diagonal. K. Good. Thank you. Let it be K. And if I just give this one a name X, this matrix. All I have to present, all I have to show you to convince you that the inverse for K will be X, I have to show you that this identity, that the CX product, or this time KX product, is identity. And that is easy because now you sub in what you set for K, you sub in what you set for X, that's a substitution. You put the brackets in the right order, and properties of the matrix multiplication allows you to put the brackets in any order you wish, and it's just your smart choice which way to put the brackets in. That's my choice. The inner product within these brackets, it returns identity because B inverse is the inverse of B. So you end up with something like this, and then because identity multiplied by A, just simply A, and that is another identity. And that's half of the proof, in fact, because look at this. I just have a matrix K. I suggested a candidate for the inverse, and I proved you that the product like this returns identity. The second half will be a similar argument, which will show that the product in the other order even though I have to use K here again, it will be identity as well. And that's all there is to the proof of this lemma.